So, for the first session of the afternoon, we'll listen to a talk by Caio Macedo from the University of Para, but inside Polish, right?
Yeah.
And he will talk about Axion Weak Leaks, dark matter-driven inspirals. So, please, you have the floor.
Okay, thank you. So good afternoon, everybody. I hope you are well fed, but not so sleepy. I will try to make things excited, but I may fail a little bit. But to start, I will follow the example of Haroldo and show you some pictures of Salinopolis, which is a wonderful city. It is a small city, indeed. It's the city I'm currently working. Has nice beaches, a nice weather. Usually it's a very calm city, apart from the summer, in which everyone from Belém goes there, and it's a very turbulent place to stay. But so Carolina already told you that we are organizing a school there in 2 weeks from now. If you are around, you are very welcome to participate and join us. Okay. So I will discuss today, I forgot to talk about the title. I will talk a little bit about this work that I did in collaboration with Francisco Duque, Vitor Cardoso, and Rodrigo Vicente, entitled Axion Weak Leaks, Dark Matter-Driven Spiral. And it will be clear in a minute why I call this weak leaks, because one of the reasons that we start to investigate this type of system is to analyze, apart from gravitational waves, how dark matter might leak from spirals, from black hole binaries or whatever configuration that you have in a binary system. So to start, I shall speak a little bit about the axions and what are these particles and what are these axion-like particles as well that we have been discussing in the past weeks. What happened to black holes when you have these environments, these like bosonic environments in which they are moving around, because we know dark matter is out there, and if these dark matters are formed by axions, we have to understand how black holes and other compact objects move around these environments. I will discuss a little bit about what we do to find the physical consequences of these systems. In particular, how do we solve black holes plus these additional fields? Unlike what we see in the past few days, I will try to do everything perturbatively because the aim that we have in mind is some possible future detection from LISA-like system. Okay, and then in the end, we will reach the point to discuss actual numbers, what we did find by computing this flux, the evolution of the system, and what we can learn from binaries formed around axionic compact configurations. Okay. So to start, let's discuss a little bit the axion and the string XPath. So axions are essentially, they arise as a possible solution for the strong problem in the standard matter physics. So you have some additional term in which you have some symmetry breaking. And in order to fix this problem, this CP problem, you promote some quantities that you have to dynamical fields, and this naturally give you a pseudo-scalar field that is ultralight. And therefore, as a consequence, you have, from beyond standard models, this ultralight scalar field. And why is that important? So the mass is usually around this value here. And this is important because a lot of particles that we have in the standard model are not in this range, are far from this, much higher masses. And these higher masses that we have in the standard model physics does not have direct consequences to astrophysical black holes. We will see in a minute why, right? But apart from axions, we discussed a little bit dilatonic fields and other types of configurations that arise from essentially Kaluza-Klein mechanism, which is you do a dimensional reduction of your space-time, and as a bonus, you have an additional fields that arise, and there are plenty of these fields in different types of string theories, and these fields can have masses that goes up to 10 to minus 33, which is the Hubble limit that we have in our universe. Okay. So essentially, we have that these particles, these ultralight fields, fits very well many of the phenomenology, the data that we have on dark matter, which is very good because it gives you a kind of natural candidate, a simple extension of your standard model that solves a lot of problems. Okay. But as I told you, ultralight scalar fields or bosonic fields have a profound impact in astrophysical black holes. In particular, rotating black holes, we know that if you throw a bosonic wave into these rotating black holes, it can amplify extracting energy and angular momentum of the black hole. This is what we call superradiance. Luis yesterday gave this remote talk that showed some systems in which you can have superradiance. So this is the amplification factor for different types of fields. You have a scalar field, electromagnetic field, and the gravitational one. So for the scalar field, the amplification is not so violent. You get an amplification of at most 0.4% of the incident wave, right? Nonetheless, even though you have this small amplification, this type of phenomena can bring what we call superradiance instability. In particular, this was first investigated by Teokolsky and Press, because if you confine this radiation, you can have like repeated superradiant process to amplify this radiation inside this cavity, which was essentially what Carolina discussed this morning in analog black holes. And eventually, you have an exponential growth of your field that's inside this cavity. This exponential growth comes when you look for natural modes of this cavity plus black hole, and you find some unstable modes, right? The growth factor is not so big, but it is indeed there. So you have instability, and these fields can grow around these black holes. So as Carolina told us, and that's called black hole bomb. So you can kind of construct a bomb if you take a black hole, put inside a bottle, confine this bottle, and then you have a black hole bomb, right? So essentially it's that. So how long does it take to the bomb to explode? That's another problem, because the time scale is a very long time scale. So it's a grenade with a timer that's very slow. It's maybe not very efficient, a way to construct the bomb, right? So a natural confinement, as Carolina told us, is to put a mass in your scalar field, because then you get rid of this artificial boundary that you have around your black hole, and you have the mass term that confines some frequencies within the region of the superradiant, the region of the black hole. And then you have amplification, and again, you have this instability, which is characterized by this imaginary part of your mode becoming positive. And if you see the number here, you will work out that this thing is more efficient, this instability is more efficient when you have the Compton wavelength of your field being approximately the value of the event horizon. So this is like a rule of thumb. You estimate what would be the mass of the field for the instability to be relevant for your black hole. And if you do that, you will find that this massive field should have masses. From this equation, you get this one. That is of order of 10 to minus 11. So, okay, thank you very much. Thank you. So you have 10 to minus 11. So that is to say that you need to have very, very light scaling, indeed ultra-light scalars. So as I said to you, no standard matter particle has that. So that's why it's interesting. That's why we had a lot of new works discussing these consequences of having bosonic fields around black holes, because now we have some proposals that are physically motivated that can give you relevant evolutions for your black holes, so for your physical black holes. Yep. Okay. So what happens when you have these ultralight fields? So this is a plot from work by Richard Brito, Vitor Cardoso, and Paulo Pani, but you can find similar plots elsewhere, in which they essentially start with a rotating Kerr black hole, give it some time, and see how it evolves in a adiabatic regime. So what happens is that essentially, eventually, this black hole, it has some of its mass transferred to this cloud of scalar fields because of superradiance instability. It reaches a critical point, and then the mass decays either by accreting to the black hole or dispersing away, right? But the mass can stay there, depending on the situation, for a sufficiently long time to impact the physics of your black hole, right? And of course, there are other people that have been doing this experiment in a non-linear regime, and they found some similar things. Okay. All right. So one of the consequences of having these fields around black holes is that you can grow the fields surrounding the black hole almost spontaneously. Through instability, these fields grow. But another consequence of having ultralight scalar bosonic fields is that they can condense and form these bosonic stars, these boson stars. Many people discussed boson stars and how they form, and I think Uli just before lunch was discussing about this, so I will not stay very long into this slide. I just want to show that these boson stars can come in many flavors. Here I show 3 of them, which is this scalar boson star, which are the mini boson star, when you have just the mass in your self-interact potential. You can have oscillatons that are formed by just real fields. They are unstable, but they can live a very long time. So essentially, you consider them stable because the lifetime is huge. But you have also these Broca stars, and each one of them have these mass ratios relations that can exist and so on. We all know that, and as I told you, that we had a lot of boson stars in the symposium. I didn't just realize that BS can mean other things, but it's not. We didn't have a lot of BS in the symposium. The symposium is wonderful. We had boson star. Sorry, it's problem with acronyms. And what we can expect when something moves through this medium. Right, so now we have a black hole with a scalar cloud around it, or you have a boson stars that arise from just these ultralight scalar particles. Okay, then if you have a black hole moving through this cloud of particles, of fields, part of these fields you expect that part of this field is transferred to the black hole itself through an accretion process. On the other hand, you also expect some momentum transfer to the black hole as well, right? And people have been computed this through nonlinear routines, numerical relativity routines, but also from a perturbative regime in which you consider just a test scalar field propagating the black hole direction and seeing how much of how it is the force that you feel that your black hole feel in the presence of this field. So if a black hole moves through this field, it will feel accretion and will feel some transfer of momentum that we call both of them combined. I mean, this part is a bit not very clear if you can distinguish both, but in the end, there appears a force into your black hole that we call dynamical friction, right? And in fact, if you are not used to this picture being called dynamical friction, it's funny that from the relativistic formulas that you get from a plane wave hitting a black hole, you can get the usual Chandrasekhar formula. For those that know this, is the Newtonian formula to compute this dynamical friction force when you consider a particle moving into a uniform in a uniform fluid, right? So one consequence that we have is that due to the existence of these clouds, it will feel a dynamical friction that will essentially break the motion. But there are other things that arise that are very interesting. For instance, if you consider this cloud around the black hole, this cloud, this black hole that has this cloud can be a part of binaries, right? And many people have investigated this in the past, that when you consider disturbance in the potential generated by this companion, you can have transition of energy levels in the cloud. And this transition is due to transfers of energy and other things in angular momentum from the particle and the black hole cloud system, right? This was computed through many works, like considering hyperbolic encounters, considering circular motion, eccentric motion, and so on. And in fact, this can have a consequence in how you observe how this system evolves if you compare to the standard gravitational wave-driven signal. So basically, this work by Tomaselli et al. And also Boskovic et al., they computed the evolution of the inclination plane of the binary and the eccentricity when you consider some transitions in your levels, right? So then you see that the eccentricity and inclination, it evolves into a direction, and it can have some non-negligible non-negligible eccentricity at the final stage of your binary. And maybe that's one of the points that people are starting to look into binaries with eccentricity, because there are mechanisms which can give you eccentric binaries. And also one interesting thing that happens when you consider such system is, which is also related to dynamical friction, is what these people call ionization. But essentially, ionization is emission of the scalar radiation in your system. But so if you compare the emission of scalar radiation, the ratio between this scalar radiation and gravitational radiation, you will see that the number is quite large. And you have these steps here that essentially comes from the fact that radiation, this type of radiation is not emitted continuously, but you have each multipole being relevant at a given frequency. So in order to excite a different multipole, you need to have an orbital frequency that has certain values. So there is a type of selection rule here. So they call ionization because when you hit this, you excite this type of radiation, and then the system leaks a little bit, similarly to what you have when you have like a decay of level in an electron in hydrogen atom. Okay, so you can see that the system is leaking. So on the other hand, what we have, so these are binaries, these are moving black holes through mediums, and this is important because we now know that we have this channel of this astrophysical channel that are gravitational waves in which we observe these binaries. So if you have an environment, if you have something that is there, we should take into account to properly describe this type of motion. And here, we shall focus in two types. So we will see this black hole plus cloud. So given that you have a black hole and you can have this cloud growing around the black hole, you may ask, what are the relativistic features that we have in the emission of gravitational waves and scalar waves and axionic waves that you have in your system? So we will consider a smaller companion orbiting this system, so the black hole mass is much bigger than this one. But we will also see the case of parasitic black holes. What this is? What is this? So if you have a boson star, you can conceive that this boson star will accrete matter. So imagine that you have a supermassive boson star or even a galactic halo. You can have a smaller black hole forming in the center of this boson star. Or if you want, if you imagine this halo, in which is one of the things these ultralight fields describe, this halo can simulate what we have in our galaxies, right? Which is a black hole plus a dark matter distribution that scales over the distance of the galaxy. Right? And then you put something to orbit the system. And you see what the equations can show you. And to solve for the system, to obtain its solution, we will look into the Einstein field equation. So the formalism is relativistic. On the other hand, unlike what Yuli showed for us this morning, I'm concerned mostly with perturbative approach, which makes sense because we have an extreme mass ratio scale here. And then what we do essentially is consider a background scalar, or a background metric plus a background scalar field, and then add some perturbations on top of it. So these perturbations can then be separated into the angular decomposition so that you can achieve the radial master equation and so on. And this will describe essentially, these perturbations will describe the waves, the disturbance that you have. And if you want more details, you can look into the paper itself. But then you plug that into the Einstein's equations, work out your fields, the background plus perturbations, solve them. It's not a very simple system, I should say. It's a simple system that is coupled, but you can solve that through the usual methods that you do in differential equations. And you obtain the solutions and compute the radiation and so on. So as I said to you, for the black hole plus clouds, what we do is you background metric is Schwarzschild. So that essentially, when you do that, you impose that the field is small enough just to be considered as a profile on top of it. So Carlos mentioned in his talk that in some extreme case, you can have the cloud being like 20% of the mass, of the total mass of the system, black hole plus cloud. If you extend that over a very large scale, this means that your field has a very low density. So you might as well consider like almost a superposition. But what we do is that we put Schwarzschild, and then we put the background scalar field as the spherical profile for the cloud. This is the spherical profile is not very well motivated because usually the superradiant growth is starts with dipolar profile, but it's just to understand a little bit the influence of this scalar field, this background scalar field, in the fluxes, in the energy emission of these binaries, and see what we can extract from that. For black hole plus boson star, we consider like this PN approach. So you have the potential, geometric potentials, and then you see how you can compute it perturbatively. So essentially this phi here is, is the background field that you have only dealing with the boson star. And then when you work out your equation, you will see that the metric potential A will be given by this part, in which this U is computed through like, there is an integral I forgot to include here, but you can compute that from the background scalar field. This M is the mass function that we have usually, so you have the black hole mass plus some term that comes from the scalar field distribution. And at some limit, so very far from the black hole, this looks like a superposition of a boson star plus a black hole at the center. Just the sum of the two in the potential, what you get usually from the Newtonian description, right? Because in the Newtonian physics, things can get, a superposition works, okay? We also checked that this is consistent with superposition at large separations. And then you solve for this system, and you compute these quantities, which is the flux of energy, in which this S stands for phi or G, which is the scalar or gravitational radiation. You have this Noether flux, which is considers essentially how many particles flow from your boson stars. From that, you can compute the rate of change in the orbital energy, which is given by this quantity here. You have the scalar part of this rate of change. You have the gravitational part, and to compute how the change of the orbital, to compute the orbital energy change, you just add the two together. And this part here is essentially the part of the energy that is transferred from and to the cloud that you can compute as well. So because your system is composed by the particle, the energy, the gravitational energy that is leaving, the scalar energy that is leaving, and the energy that changes inside your structure. Okay, so you have to consider that to properly account all of the things. And then you can test that with just a boson star. So we computed the flux of the bosons of the particle orbiting a boson star, and you can consider many of the mass of the boson star. And so I forgot to put the unity, but the unities are unities of the mass of the total configuration, the boson star, and the units of the mass of the field. And you see that you have some peak that is very near where this ionization starts. And then it decreases until it gets to very small quantity, until it goes to zero at the center. So this is the radius of the orbit, and this is the flux, the scalar part of the flux. This dotted line here essentially is the numerical result, and the solid line is an analytical result that you get from just Newtonian boson stars that we are considering. So, and it makes sense because the analytical results approach very nicely the numerical results in the less compact case, while in the most compact case you have some deviation here. But it's good that we have some analytical description. You just need to compute the numerical amplitude of your background field and your orbital frequency to compute these fluxes. It's just compute the background. You don't need to integrate the perturbation equation every time. And then when you put a black hole in the center, you have something like this, right? So in red, what you have is the scalar radiation. So this bigger one is the dipolar one, followed by the quadrupolar, and then the octopolar flux. The gravitational part, this bigger one, this blue one, is the quadrupolar gravitational wave flux, and then you have the octopole here. So two things we see happens here. that is happening here. The first thing that we notice is that here you have some very narrow peaks that essentially are resonant configurations. These resonant configurations are those phenomena that occur when the companion transfer energy to the cloud states. So there are those shifts that occur when you compute the transition of levels essentially are these resonant configurations. So you don't have emissions of scalar waves, dipolar scalar wave, of quadrupolar scalar wave when you have these peaks here. These are relativistic correction only, but these are related to the modes of the star. So you put a companion that emits in the same frequency of the natural oscillation of your system, you have these oscillations, this peaks profile. The dotted line here that you have is essentially the quadrupole and octupole formula that are analytical. And what you get is that you do have some convergence at higher frequencies here, which is good. The dotted line here are the analytical formula that I just showed you that works for the boson star case, but it doesn't work for the system black hole plus the particle. And we have a clue of why this doesn't work for this system here, essentially because you have higher energy emission in this region, but also to compute this problem, we didn't consider the black hole at all. You just consider the boson star. So at larger distance, the system doesn't see the boson star. Okay. Right. But yeah, but you see an increasing of the radiation when you go very close to your to higher relativistic orbits. Okay. And one thing that is interesting here is that you see that in this part, the flux from the axion part is much bigger than the gravitational wave. So you have some region in your parameter space in which the axion flux dominates and actually drives your evolution. And we went on to look if you could see, like in Lisa band, some deviation, and we see that above this, it depends, of course, on the mass ratio, depends on the mass of the cloud, of the boson star, and the mass of the black hole at the center. But above this line, and for this mass ratio, you could have, in 4 years, in a mission of 4 years observation, you could have some deviation that could be potentially seen in Lisa. So we did the same for the system of the cloud, and we found as well that, so these are the gravitational fluxes and the axionic fluxes, and we find that this flux also can be observed in a potential future. So just a final remarks, ultralight fields are found everywhere beyond the standard model physics, so these have consequence for astrophysical black holes. As I said to you. So this evolution of these binaries can potentially be tested in the future. And a large fraction of energy is due to action. So it really leaks in a sense. So once again, this is the Salinopolis, we have the school. And thank you all for listening.
Thank you very much for the talk, Caio. Are there any questions? Yes, please.
Thank you very much for the nice talk. It's just a curiosity. In some papers, I saw the plot that you show the mass-radius relation, and I saw that for the oscillaton and the boson star, the relation is similar. It's very similar, actually.
It is. Yeah.
There is a reason behind that? Because I know that for the boson star we have complex fields, which means two real fields.
Yeah.
But I don't know if...
Yeah, I'm not so sure about the fundamental reason, but solitonics are a bit, oscillatons are a bit trickier to find, right? Because you have to make a Fourier expansion of your fields, and then maybe there are more degrees of freedoms there that makes the system similar. But I'm not sure about any fundamental reason why, especially in the in low compactness regime, they're almost the same, right? And even the maximum mass they are a few percent off, right? But I'm not sure about any reasons why this would be like very similar. Okay. Thank you.
Other questions? Maybe I have a quick one. Okay. So at the end, you were mentioning some difference in the cycles for Lisa.
Yeah. Yep. Is this one?
Yes, I think. So, so above the line, you see more than one cycle of difference.
Yeah.
Okay. So, but is like one cycle? Is it?
It's not that much. Yeah. But the problem is that we are looking to the Lisa regime, which is well within the configuration. So it is in a region in which you already have like dominance of gravitational wave emission. So in this part of the movement, the gravitational wave dominates. So that's why you get this small deviation. But in the whole spiral, if you take from 1000 m distance, you get more cycles. So if you could observe like a low frequency regime beyond the Lisa range, maybe you could see more than one cycle.
How low is the frequency? Is it something like would be PTA or?
I have to check, but it's the same that you have in supermassive black hole binaries. So if you take a supermassive black hole plus a companion. So for Lisa, we took like the distance was 15 m. So yeah. So I don't call my mind that frequency.
Thank you.
So if there are no more questions, I think we can thank the speaker again.
Thank you.